In this lecture, we're going to take a look at what it means to find the derivative in various directions for functions of more than one variable. Before we begin, again, we use the paradigm that has been given to us with one-dimensional calculus, in which we analyze what a derivative means in one dimension. So imagine you have an unevenly heated metal wire lying along the positive number line. Let T of x be the temperature in Fahrenheit, degrees Fahrenheit, of the wire at any point x centimeters to the right of x is equal to 0. And we've taken the temperature at various locations along the wire at 0.5 centimeters, 1 centimeter, 1.5 centimeters, and so on. If we were to ask the question then, given the function t of x, what is meant, or what is the meaning of t of 2? To answer that question, we would be looking at the wire at x is equal to 2 centimeters to the right, 2 centimeters to the right of 0. And we're asking what is the temperature at that specific location, 2 centimeters. So this would be the temperature two centimeters to the right of 0, of x is equal to 0, which would be, according to the table, 94 degrees Fahrenheit. Since at 2 centimeters to the right of 0, the temperature is measured to be 94. If we wanted to estimate the change in the temperature as we moved around from between 0 and throughout the wire, if we wanted to find how quickly the temperature is changing at the location 2 centimeters, that would mean that we would have to take a look at the derivative of t, which would indicate to us the rate at which temperature changes with respect to distance. And remember that this is an instantaneous measurement of the rate of change. In most cases in the real world, we're never going to be given a continual measurement along an entire length. So what we would end up having to do is estimate the derivative at that particular point. We can estimate the derivative in a couple of ways. One way we can do this is we can find the difference quotient around 2. So we could do, for example, t of 2 minus t of 1.5 all divided by 2 minus 1.5. That would be one way that we could estimate what is how quickly the temperature is changing with respect to distance around 2. We would find by looking at the table that t of 2 is 94 degrees, t of 1.5 is 87 degrees, and 2 minus 1.5 would give us 0.5, or a half. So we would end up with 7 all over 0.5, and 7 in the numerator is in degrees Fahrenheit, and remember that in the denominator we are measuring the wire in centimeters. So our rate of change is going to be given to us in terms of degrees Fahrenheit per centimeter. Performing the division, we would end up with 14 degrees Fahrenheit per centimeter. which is an approximation around 2, but this is not the only approximation that we are doing. This is not the only approximation that we're doing. This is a backward approximation starting at 2 and going backwards to 1.5. We could also say, for example, that we started at 2.5 and go backwards to 2, and that would also give us an estimate of what the derivative is close to 2. So we could also do t prime of 2, doing a forward difference, which would be t of 2.5 minus t of 2 all over 2.5 minus 2. T of 2.5, according to the table, is 97 degrees Fahrenheit. And of course, T of 2 we measured to be 94. All of this divided by 0.5. And remembering that the numerator is in terms of degrees Fahrenheit and the denominator is in terms of centimeters. The end result will give us 3 over 0.5 degrees Fahrenheit per centimeter, or 6 degrees Fahrenheit per centimeter would be the approximate rate of change around 2. You could continue with these sorts of differences. You could do, for example, you could do the temperature at 2.5 estimated with the temperature at 1.5, and that would be approximately an estimate on the derivative at 2 centimeters as well. These sorts of games are often played by engineers depending on the situation and whether or not the physics of the matter dictates this. In this particular situation, we don't know anything about the flow of the temperature, so it doesn't really much matter that that we do forward or backward as being more accurate, albeit things are going to flow from hot to cold. So since it is warmer at 3.5 but cooler at the ends, we're flowing in both directions as in some sense. So since we have two different measurements of the temperature at approximately 2, we can average them, and so we could say that our T prime of 2 averaged could certainly be 14 plus 6 divided by 2 to get a central difference, and this would be 20 over 2, or 10 degrees Fahrenheit per centimeter. Understand that in actual applications, you will never have an exact answer. You will always be estimating, and so you have one way of estimating, which is to take different measurements and then average them together to get a general idea. One thing that we could probably say is that since it is cooler on the end closer to 0 than it is on the end closer to 5 centimeters, that the heat is going to be flowing more into the direction of the cooler side of the wire, which is why we would expect that the backward difference is going to be greater than the forward difference. If we wanted a general idea of how temperature is changing throughout the wire, this is why an average of the two is a good idea. You could continue this sort of game by looking at other values or other derivatives as well, but it's important to understand what the derivative is telling you. So a little explanation is that when we did t prime of 2 is equal to t of 2 minus t of 1.5 all over 2 minus 1.5, the name for this in numerical mathematics is called a backward difference method. And it's used by engineers and physicists to estimate derivatives based on data as I've given it to you here. The backwards difference method would be ideal because of the fact that temperature we are expecting is going to flow towards the end that is cooler. However, since both ends are cooler than the middle, then the other method, t prime of 2 approximately equal to t of 2.5 minus t of 2 all over 2.5 minus 2 is called a forward difference method. And it is giving, both are giving us approximately the rate of change of the temperature as we move along the wire. And that's the key, that we're moving along the wire and we're moving in a very specific direction, which is in the one-dimensional direction. As we move between being at 2 centimeters and going to a cooler end, or going to an even cooler end from 2 centimeters, the rate of changes we would expect would be different. But it is going to depend on whether we're moving towards 0 or whether we're moving towards 5 centimeters. This idea of directionality, of course, becomes even more sophisticated as we start looking at situations that involve multiple dimensions. For example, let's expand this concept of a heated wire to something that is multidimensional, such as a heated plate. So suppose I have an unevenly heated plate, and we're going to imagine that the plate is lying in the first quadrant of the xy plane as I have drawn it here. Let T of xy equal the temperature in degrees of Fahrenheit of the plate at any x location, and the x locations are given to you along here in the table, and they're to the right of the origin, and any y location which is up from the origin. If we were to ask ourselves then, what is meant by T of 3 of 2, we would respond to this by saying that T of 3 of 2, T of 3, 2, first of all, would mean specifically this, that if we went over 3 and up 2, we would be in this location right here, where I have placed my red dot. And the temperature at T of 3, 2 is going to be 145 degrees Fahrenheit. It's the temperature when we move 3 to the right. So it's almost like we have a wire that runs along in the x directions, and we have wires that run along the y directions. And so when we run along the wire, that the two wires that intersect at this particular point, 3, 2, we discern that the temperature at that point of intersection of the two wires is 145 degrees. I think it's important that you imagine, for the purposes of this example, two wires that are sort of running in perpendicular directions, one parallel to the x-axis and another wire that is running parallel to the y-axis. So it's very much like the problem now that we just did in the first example, except we have two wires that we're taking into account. And the reason that we're only looking right now at these two wires and not maybe a wire that's going diagonally through is because right now we're just mainly concerned about how do we account for the coordinate directions, the x and the y directions. So one question we could ask then, what is meant by t of x2. And what that would mean is we are going to imagine a single wire located at the position where y is equal to 2. So we're fixing the value of y, and that's an important concept that you need to get, that we're fixing the value of y at 2, and we're looking at how the temperature varies as we change the value of x. And so this would mean that we're going in along the x-axis, or that the x values are changing. We imagine a single wire located at y is equal to 2, and we have different temperatures as we travel along the x-axis, or as we travel along that wire. Specifically, you could then say that we could define a whole new sort of function, if you would. We could say that the temperature is now u of x, which would equal the temperature when y is equal to 2, specifically. And since y is always equal to 2, x is the thing that can vary, so we can look at x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, 4, and 5. And we have, based on the table, we look at this line specifically, since this is the measurement of the temperatures when y is equal to 2. And so our measurements are going to be 100. Let's see if I can get them in the same screen. Our measurements are going to be 100, 110, 120, 145, 190, and 170 degrees. Now remember, this is just one location on this plate, and the reason we're breaking it up this way is because it's easier for us to be able to imagine what's happening along the wire, since that's the paradigm that we've set up here. We know how to work with this. The plate is a massive space, so we need to break it up into parts that we can actually manage, and one of those is to make sort of the construct that we have several wires that are one-dimensional. And so we're fixing the value of y and looking at one of those particular wires, and we can then talk about the derivative of that wire in a meaningful way. For example, we can now say, first of all, we can say that u prime of let's say 3 specifically, just like in the previous example, would be approximately, well, we could do the backwards difference method, where we estimate the derivative by taking the slope, as it were, using the point behind 3. So we would do u of 3 minus u of 2 all over 3 minus 2. And so this would be 145 minus 120 all over 1, which would equal 25, sorry. No, 15. Oh, 25. 25 degrees Fahrenheit per centimeter. Remember, this is a rate. So as we move along the wire, when we get to the point 3, the rate at which the temperature is changing is going to be 25 degrees Fahrenheit per centimeter. And it's in a positive direction, which means as I move towards 3, the temperatures should be getting warmer. Does that make sense? It does, because next to 3 is an even warmer spot still, so the temperature is increasing as we get to that particular point. Now, this is directionally motivated. because we're only moving horizontally at this point. We can do play the same game by taking the forwards difference, and the forward difference would be the following. It would be that u of 3 would be approximated by u of 4 minus u of 3. That is, we estimate the derivative by taking the point ahead of 3 centimeters. And so in that particular case, we would end up with 190 minus 145 all over 4 minus 1, which would equal 45 over 1, which would equal 45 degrees Fahrenheit per centimeter, which is an even bigger rate of change, but we would expect that, right? Because at 4 centimeters, it is significantly warmer than it is at 3, and so we would expect that the temperature, since this is cooler by the second law of thermodynamics and heat transfer, that this is going to start to get warmer because it's next to a spot that is rated at a higher temperature. So when we go to the forwards difference method, we see that the rate of change is even greater. We can, of course, average these two to get a central difference or an idea of, in general, what's happening at that particular spot. Now note that this is the derivative specifically at 3. It doesn't hold for any other point. It's what's instantaneously happening at 3, and so we can take 45, add it to 25, divide by 2, and we would get that the average is going to equal 35 degrees Fahrenheit per centimeter. And this would be the average rate of change. Of the temperature. But remember that at the point 3, 2, going back to this picture here, and we're going to be scrolling up and down for the next few examples. At this particular point right here, there are 2 wires that sort of intersect. One wire is where I'm fixing the value of y at specifically 2. But then we also have this vertical wire here where we can fix x at just specifically 3. And so we can also define another function. We can define the function v of y to be T of 3y, which is going to be the temperature along the wire. And I'm using this concept of a wire as sort of a tool. It is not really a wire, it's just a mental construct because it's easier to imagine a straight line going down that path. And we're going to imagine the temperature along that particular wire that is fixed. And that's the key word. It is fixed at x is equal to 3 centimeters. And so if we were to sort of write the chart now for just those values, we would find the following. We would find that when y is 4, we're at 125 centimeters, 125 degrees. When y is 3 centimeters, we're at 135 degrees. When y is 2 centimeters, we're at 145 degrees. 1 centimeter, 160, and at 0 at 160 as well. And we're going to call this function v of y because it's dependent on the y variable. It's dependent upon where we are along the y-axis, or along the where we are along the y-axis. And so if we're fixing x to be 3, the values that I've read to you are the values that run along in the y direction at x is equal to 3. So we're moving along this wire right here on this coordinate plane. So we could talk about v prime of 2. V prime of 2 We could also do forward and backward difference as well. We could do v of 3 minus v of 2 all over 3 minus 2, which is an interesting value because v of 3 is 135 and v of 2 is 145. So unlike the previous examples, we end up with a negative rate of change, which means that at 3, that when we move in the y direction, that the temperature is getting less. We can use the forward differencing method as well by doing v of, actually this is the, not forward, this is the backward difference method. So this was the forward one, because we went one value ahead, and now we're going to go one value behind. So this is the backward. And when we do that particular differencing method, we will end up, and I'll let you plug in the values in the chart, from the chart, you will end up with negative 15 degrees Fahrenheit per centimeter, which means that the temperature is decreasing in the y direction. And this is interesting because directionality mattered, that if we were moving in the x direction, the temperature was increasing, since at this particular point we estimated the rate of change to be about 35 degrees Fahrenheit per centimeter. But moving along the y direction, the temperature is decreasing. So directionality mattered. The temperature changed in two different ways. The temperature is decreasing at 3,2 along the vertical wire. So this gives us a concept of derivatives in more than one variable. For right now, the main way that we're going to approach this is specifically this. The derivative can be taken in a specific direction, and for right now we can find that derivative by fixing one of the variables and sort of creating a line in that particular direction, and then using the same differentiation techniques that we have learned previously from one-dimensional calculus. And so we can conclude the following. This demonstrates that we can take the derivative of a function f, and right now we're specifically looking at when we have R2 to R. The same principle, of course, will hold in 3 dimensions and in more than 3 dimensions as well. And we can take this derivative in 2 directions. But these are going to be 2 different derivatives. And that's important to understand. These are 2 different derivatives. They're not the same derivative. We hold one direction or variable constant. And consider the change in the other. And so when we were looking at u prime of 3, this is essentially the derivative of u with respect to x, since u was representing the temperature at a fixed value of y, and this is the derivative at x is equal to 3. We are going to denote this in the following way, we're going to denote this as the derivative of t with respect to x at 3, 2, or dt dx. This is called a partial derivative of t with respect to x, and this is at the point 3, 2. And so when you see this here, tx, what it means is that we're fixing y, we're holding y constant, and differentiating x. V prime of 3, well actually V prime of 2, would have been dv dy since v ran in the y direction, and this would be specifically at y is equal to 2, and we will denote that with t with a little subscript y at the bottom at 3, 2, or with this funny looking d again, but with a dt dy, and it's still read as d even though it's curly d. So dt dy are partial t partial y, and this is at the point 3, 2, and this is the partial derivative of t with respect to y at the point 3, 2. And so this is how our concept of differentiation in more than one variable, that we are going to hold, in this particular case, hold x constant, and take the derivative with respect to y. These concepts of differentiation are made clearer to us when we take a look at the limit definition of the derivative. And so our limit definition is going to be the following, that if the limit exists, we define the first partial derivative at, let's just say, the point AB as the following. We use this curly d of f with respect to x at the point AB, just as I'd written previously, which we can also denote with the subscript x of AB. And we will say that that's equal to the limit as h approaches 0 of f of a plus h, comma b, minus f of ab all over h. And so you can see that we're holding y fixed. In both cases, both functions are being evaluated at y, but at different values of x. Likewise, with the partial with respect to y at the point AB, we can denote it with this, the curly d's, or the subscript y at AB, and that would be the limit as, and this we would have to use another variable, k approaching 0, of f of a b plus k minus f of ab all over the value k. And those are the derivatives if we're looking for the derivative at a specific value In general, however, the derived function in terms of x and y would be found very similarly as it was in Calculus 1, where we take the limit as h approaches 0 of f of x plus hy minus f of xy all over h, and the partial derivative with respect to y would be the limit as k approaches 0 of f of x y plus k minus f of x y all over k. And you can see it here a little bit more clear. We're holding y fixed. X is the thing that is varying for the partial derivative with respect to x, or with the partial derivative with respect to y, x is being fixed and y is the thing that is allowed to change. This, of course, is not how you're going to do differentiation. We just are going to look at a few examples to make sure that we understand this concept of holding something fixed and varying the other variable. You could think of it much as taking an ordinary derivative, as you did previously, and then treating one of the other variables as a constant, not as a particular variable. So, for example, if f of xy were to equal x squared plus 4x minus 10xy plus 3y squared plus 1, if we wanted to find the first partial derivative of f with respect to x, I'm going to write both right now so that both forms of the notation right now so that you get used to how it is going to be presented to you. For right now, just looking at the limit definition, this would be the limit as h approaches 0 of f of x plus hy minus f of xy all over h. And so all of the x's are going to be affected when we do f of x plus hy, not the y values. So we would get x plus y, h, the quantity squared, plus 4 times x plus h, minus, now here we would have 10 times x plus h because x is the variable that is being changed, but y is the variable we're holding fixed. And so it would be minus 10x plus h y plus 3y squared plus 1. Then subtracting off the precise function x squared. I just lost my 1. Then subtracting off x squared plus 4x minus 10xy plus 3y squared plus 1 all over h. And you're going to have to do a little bit of algebra to work this problem out. I'm going to give myself more room so that I get the limit as h approaches 0 of x squared plus 2xh plus h squared plus 4x plus 4h minus 10xy minus 10hy plus 3y squared plus 1 minus x squared minus 4x plus 10xy plus 3y minus 3y squared minus 1 all over h. The x squareds are going to cancel out. The 4x is going to cancel out. The 10xy's are going to cancel out. And then notice this is what's interesting. Remember, y is not changing, so this 3y squared is going to completely go, and so will the 1, just as we would expect in any derivative. The derivative of a constant is going to be 0. But in this particular case, since y is being held constant, the derivative of 3y squared should also be anticipated to be 0, and so that's why we would get the cancellation there. So from this, we will end up with the following. We will end up with the limit as h approaches 0 of 2xh plus h squared plus 4h minus 10hy all over h. And then, of course, dividing through by h, you would simply end up with the limit as h approaches 0 of 2x plus h plus 4 minus 10y. And taking that limit, you would end up with 2x plus 4 minus 10y as your partial derivative. Try this on your own for the partial derivative of f with respect to y. I'll get it set up for you. We know that this, using the definition, this is going to be the limit as k approaches 0 of f of x y plus k minus f of x y all over k. And so you would plug this in, and I mean, x is not going to change, 4x is not going to change, but the y will. So you will get minus 10xy plus k, and now you get 3 times y plus k, the quantity squared, plus 1, subtracted by the original function, x squared plus 4x plus 10xy plus 3y squared plus 1 all over k. Maybe take a moment and pause the video and work through this to make sure that you end up with negative 10x plus 6y as your answer. So how do we do this in practice? How do we take the partial derivative? So in practice, we're going to find df dx by holding y constant. And of course, this also applies to functions in more than two variables, and n variables. So if we had x, y, and z, you would hold y and z constant, and then we would take an ordinary derivative. What you should see with respect to x, what you should see in this statement, or by writing the partial of f with respect to x, the partial derivative, is that we're allowing x to change. So it's changing in the x direction. It's all going to be in terms of directionality, so that we're looking at how the function changes along a horizontal wire. Whereas in df dy, we're allowing y to change, so you want to imagine a vertical wire. And so we're holding x constant. And take an ordinary derivative with respect to y. So all of the x values are going to then be treated like constants. All of the rules of differentiation that you learned are then applicable depending on the situation that we're in. So if we have f of xy is equal to x squared plus 4xy plus y squared minus 4x plus 16y plus 3, let's find df dx and df dy. And when I say that, when I say df, I'm referring right now in the context of calculus 3 to the partial derivative with respect to x and the partial derivative with respect to y. So for df dx, the way that this is going to be applied is as follows. Of course, all of the differentiation rules come back into effect, but you can think of this as using the traditional sum and difference rule for derivatives, where we sort of distribute the derivative to each of the terms. So you would get the partial with respect to x of x squared plus the partial with respect to x of 4xy plus the partial with respect to x of y squared minus the partial with respect to x of 4x plus the partial with respect to x of 16y plus the partial with respect to x of 3. Now, one of those is really simple. We already know that this is going to equal 0 because the derivative of any constant is going to be 0. But we also know that this term right here with the y squared is also going to be 0, because by saying we're taking the partial derivative with respect to x, we're treating y as a constant, and so too will the 16y. That leaves us then with the following. That leaves us with the partial with respect to x of x squared, plus, now our next term is 4xy, and so since we're treating y as a constant, we can pull that out along with the 4, because y is not varying. The derivative is only seeking x's. So it's the derivative with respect to x of x minus the derivative of a derivative with respect to x of, you can pull out the 4 in this case, and you get the derivative with respect to x there as well. So differentiating all of these using the ordinary differentiation rules, derivative of x squared is going to be 2x. Derivative of x is going to be 1, so we get 4y times 1 minus 4 times 1, which will equal 2x plus 4y minus 1. And that's the derivative of the function with respect to x. We can play the same game with the derivative with respect to y. I won't be as long-winded in how I write it. So we're taking the derivative this time with respect to y of x squared plus 4xy plus y squared minus 4x plus 16y plus 3. And this is why it's called partial derivative, is because we're not treating y as we did in calculus 1 as an implicit function of x. Y is an independent variable in its own right, and that would mean that this derivative is not full. It's only in one of the variables, and so it's partial. It's not of the entire. It's not encompassing the entire all of the variables of the particular function. If you were to take the derivative with respect to y of x squared, there's no y term in here, so that would be 0. There is the x would be treated as a constant, so together 4 and x would be a constant, and the derivative of y would be 1. The derivative of y squared with respect to y is going to be the ordinary derivative. It would just be 2y. And there's no y in this term here, so this is constant, and it would become 0 plus 16 plus 0. And so you would end up with 4x plus 2y plus 16 as the derivative with respect to y of f. Remember, that means we're holding y to be x to be fixed and treating y as a variable. So in some sense, we're now looking at the function here as though all of the x's are constants, but is only changing in y, in much the same way we were with the first example, where all of the where we had the one wire going down in the vertical direction, so that we were at only one x value and taking the derivative in the vertical along the vertical line. Let's take a look at another example. And remember, all of your differentiation rules from your previous experiences are going to come into effect. So let's look at g of xy is equal to the natural log of the square root of x squared plus y squared. And we want to find the partial derivative with respect to x of xy and gy of xy. One thing to note, and I'm going to do it right now, is because of natural logarithm rules, this is the natural logarithm of x squared plus y squared to the 1/2. And the 1/2 can still come outside of the natural logarithm, giving us x squared plus y squared inside of the logarithm. So that when we go to find gx, remember what this means. We're going to hold y to be constant and vary x. Now, we're going to have to apply the chain rule first, which means that we're going to have to take the derivative of the outer function, which is the natural logarithm, and then of the inner function. So remember your chain rule. This is your outer function. This right here is your inner function. And so you would end up with the following. You would end up with the 1/2 coming out. We would take the derivative of the outer function first, which is the natural log. And so we would get 1 over x squared plus y squared. And then we would take the derivative of the x squared plus y squared term, which would require the sum rule for derivatives. But if we take the derivative of x squared and just x squared alone, of course that would be 2x. Y squared, however, is going to be treated as a constant when it meets the partial derivative with respect to x. It only is seeking terms that have x's. All others it's going to sort of annihilate. And so you'll end up with the following. You'll end up with 1/2 times 1 over x squared plus y squared times 2x, which is going to give us x all over x squared plus y squared. We play the same game when we do the partial derivative with respect to y of g, where we're going to have to take the derivative of the outer function first, and then take the derivative of the inner function. The 1/2, of course, can come out. It's a constant. And so we would have 1/2 the derivative of the natural log, which would be 1 over x squared plus y squared, times then the partial with respect to y of x squared plus y squared. Now, that partial, of course, is seeking only terms with y's in them, because that is the variable that's changing. We're going along the vertical direction right now, so we're looking at that wire of the plate. And so the derivative with respect the derivative of x squared with respect to y is going to be 0, because it has no y in it. It's going to be treated as a constant. Whereas the derivative of y squared will end up being 2y. And so we end up with 1/2 times x squared plus y squared times 2y. And of course, when simplifying, we end up with y all over x squared plus y squared. Sometimes we have exponentials. Don't let exponentials prevent you from getting to your terms. Just like in the case of the natural logarithm, you're going to treat it as a composition of functions. So if I were to have, in this case, f of xy is equal to 7y e to the y over x, and I wanted to find the partial derivative of f with respect to x of xy, we would hold, in this case, y constant because we're varying x. And so we would have 7y times the partial derivative of x of e to the y over x. But the derivative of just e, which is the outer function, and if you need to mark that, that's certainly something that you could do in order to help organize your thought process. So we would then take the derivative of e to the y over x. Now the derivative of e to anything, any variable, is going to be just e itself, and so we would end up with 7y e to the y over x times then the derivative of y over x. Y, of course, again, is going to be a constant. You can just pull that out directly and get 7y squared e to the yx d dx of 1 over x, and now you can just take an ordinary derivative or apply an ordinary derivative to 1 over x, which would be negative 1 over x squared. And so your derivative in this case would be 7y squared e to the y over x all over x squared with a big negative on the outside. The derivative with respect to y would be a little bit different. The reason is, since now we're varying y, notice the following. We have a product of between 7y and e to the y over x, both of which are functions that contain the variable y. And so we would first of all have to take the derivative of the 7y and then add it to 7y times the derivative of the e to the y over x with respect to y, not x. It's important that you remember that when you're taking the derivative with respect to one of the variables, the others are going to be held as constants. They're going to be unchanging. And so we treat x's in this particular case as constants. So in the first part of this problem, we would get e to the yx times 7, since that's the derivative with respect to y. In the second one, again, you would have to apply the chain rule, noting that you have the outer function and you have the inner function. So the derivative of the outer function is just simply going to be e to the y over x. The x is going to be treated as a constant, and so you would just be taking the derivative with respect to y of y itself. And our end result is going to be 7e to the y over x plus 7y all over x e to the y over x times 1, and you can finish that problem. The times 1 is of course not going to affect it. If you want, you could simplify this further by pulling out the 7e to the y over x and just simply getting 1 plus 1 over x times 7e to the y over x. Similar definitions are going to hold for three variables. So for example, if we had a function from R3 into R, and we simply wanted to find df dx, remember what that would mean is that all of the other variables would be held constant. And so in applying my derivative, I would take the derivative of the first term, treating y like a constant would just give me a y. The second term in the expression doesn't have an x in it, and so this would be 0. But the last term, the third term, has an x, and z in this case would be treated as a constant, so the derivative of x is just going to be 1, so you get 1 times z, which is z. The same thing would hold with if you did the partial derivative with respect to y. Now y is the variable, and x and z are going to be held constant. So I would take the derivative of the first term with respect to y, and that would just give me an x. The second term, we would take the derivative, and we would end up with just z squared, and the last term has no y in it, so we would get 0 when we apply the derivative operator. df dz would then treat x and y as constant and z as the variable that varies. In this case, you would end up with 2zy plus x.
Right.
Higher derivatives can also be defined. If I were to do, for example, the d dx of the first partial derivative, this would be written as the second partial of f with respect to x, and we would write it like this. That means that we're differentiating f twice with respect to x. Notationally, this could also be written as f double prime with the two x's sort of written in the in a subscript. Similarly, you could have two derivatives of the partial with respect to you could have two derivatives of f with respect to y, which would be the second partial of f with respect to y, or written as fyy of xy. Now, what's interesting is that you can also mix and match, because now we have two different versions of the derivative, right? We have an x and a y derivative, so you could certainly have the derivative with respect to x of the partial of f with respect to y. That would still be a second derivative of f, but we would notate it as follows, putting the x before the y, so you would get, x, in this case, fyx of xy, indicating here that you would differentiate with respect to y first and then x. Similarly, you could do the reverse. You could take the partial with respect to y of the derivative of f with respect to x, and you would end up again with a second derivative, dy dx, or fxy of xy. But what's interesting, though, when we use these two derivatives is that there is a theorem that characterizes them. And this theorem says the following, and it's a very, very interesting theorem. I'm not going to prove it, but it says that if f is a function of x and y, and it really only holds for R2. It does not hold for anything else. So if f is a function of x and y, such that fxy and fyx are continuous, on some disk R, on some open disk R, or open ball, then for any xy in the open ball, you should find that the second partial with respect to x and y is going to be the same no matter which order you take the derivative. And so this is rather fascinating. It's something that I'll leave for you to play around with other functions. You would just take a second partial. So for example, when we looked at maybe one of the previous examples, like the partial with respect to y of f, and we ended up with 4x plus 2y. If we were to differentiate this with respect to x, you would get 4. But notice if you differentiated the partial with respect to x, you differentiated this with respect to y, you would also get 4. So you would end up very much with the same derivative in that particular situation. We have a very special operator in mathematics that will show up in your lives as engineers and physicists with some degree of frequency. It's probably one of the operators that I've devoted my life to representing because it controls a lot of things. It shows up in almost every application of science. This is called the Laplacian operator. And it's denoted with an uppercase delta, so it would be written as delta U. It can also be written as in partial derivative form, but what that means in partial derivative form is I take the second derivative of u with respect to x plus the second derivative of u with respect to y. In the event that we find that the Laplacian of u is equal to 0, then u, so if Laplacian u is equal to 0, then that would mean that u is called a harmonic function. So I'd like to spend a little time devoting to at least learning how the Laplacian works. So let's take a look at the following example. I want to show that for z equal to e to the x sine of y is harmonic. And you're going to find that functions that are harmonic tend to be these sort of separable type of functions where you have one function that's in terms of x and then the other function is in terms of y. That's usually a visual cue. But in order to show that z is harmonic, this means that I have to show that delta z equals 0. So in order for us to show that z is a harmonic function, we have to show that the Laplacian of z is equal to 0. That means I need to find the second derivative with respect to x, the second partial derivative with respect to x, and add it to the second partial derivative of z with respect to y, and show that those two things will add up to be 0. So let's do this. If I were to take z and I were to find the first partial derivative of z with respect to x, that is, we take the first derivative, we're going to hold y constant, so that means sine of y is not going to be varying. We're going to treat that like a constant, but e to the x is, and so if I take the derivative of e to the x with respect to x, I would simply end up with sine y times e to the x. And then in order to find the second derivative of z, I would take the derivative of what I just found, which is dz dx, which of course is the same function, so I would end up with e to the x sine of y again. The derivative of z with respect to y now, for this we're going to hold x to be constant, so that means e to the x is going to be treated as a constant, and we'll take the derivative of the sine of y. That will give me e to the x times the cosine of y. And so when I find the second derivative of z with respect to y, this is going to equal e to the x sine of y with a negative on the outside. Taking the derivatives then and adding them together, will give me e to the x sine y minus e to the x sine y, which would equal 0. And so since the sum is equal to 0, the implication is that z is a harmonic function. It's harmonic because the Laplacian, right here, defined as such, delta z, the Laplacian of z is equal to 0. Therefore, z is harmonic. Another equation that shows up frequently in applications, especially in physics, is the wave equation. And we'll do the wave equation in one variable, meaning that we're looking at a one-dimensional wave along the x-axis. But this is a wave doesn't depend on just x, it also depends on t. So let u equal x plus t, where u is a sort of a location of a particular of a string. If I were to take a string and to vibrate it, u would represent the location that this point is going to be along the x-axis at any time t. The wave equation is given to us as follows. It's the second partial with respect to u. The second partial of u with respect to t minus c squared times the second partial with respect to x. And that has to equal 0. And this is a wave equation. It is a partial differential equation, or a PDE. So this is called a partial differential equation. C, just to give you an idea of the physics, so u is the position of the string that I'm vibrating. C is going to be the speed at which the vibration is occurring, meaning at which this point right here is going to move along this wave. So it's the speed of wave propagation. These are not necessary for you to understand in a calculus class. What I want you to understand in a calculus class is how to apply a wave equation operator, or how to show that something satisfies the wave equation. So for example, show that z equals cosine of 4x plus 4t satisfies the wave equation. In this case, I'm using z as the variable and not u. So this is z, which is a function of x and t. So I would need to take the second partial of z with respect to t, which requires me to take the first partial. So the first partial of z with respect to t. Now, I know these functions can be a little bit unnerving to deal with, but you have to break them down into their parts. So you have the outer function, the cosine. Let me write that in for you. So this is the outer function, and this is the inner function. And you take the derivative of each individually. So the derivative of the outer function, applying chain rule, would be negative sine of 4x plus 4t times, then we take the derivative of the inner function, and if I take the derivative of the inner function with respect to t, remember what that means is I'm holding the other variable constant. So the derivative of 4x, since there's no t in it, is going to be 0, and the derivative of 4t is just simply going to be 4. And so we end up with negative 4 the sine of 4x plus 4t. You would then do this again. You would do the second partial of z with respect to t. And so we would take the derivative of this function all over again, treating x as a constant. I will leave the details of the differentiation up to you. Check that you end up with the following. You should get negative 16 the cosine of 4x plus 4t. And I forgot to mention in this problem, take c to equal 1. Take c to equal 1. You can then do the second partial derivative with respect to x. We would do the derivative in very much the same way. You would take the derivative of the outer function, which again would yield a negative sine of 4x plus 4t. And then you would take the derivative of the inner function with respect to x, which means you're holding t to be constant. So when I take the derivative of this term here, it will be 0, and you will end up with 4. I leave the details to you to fill in for these two, but you should end up again with negative 16, the cosine of 4x plus 4t. And now we want to see whether this satisfies the wave equation. So is it true that the second partial with respect to t minus c squared, the second partial with respect to x, is equal to 0? And I told you to take c to equal 1, so you should end up with the following. Is this true? And note that this is different than a Laplacian, right? Because it's not addition, it's subtraction between the second derivatives. And indeed it is true because they come out to be the same derivative. You would get negative 16 cosine of 4x plus 4t minus 16 cosine of 4x plus 4t, which equals 0. And so it does indeed pan out to be a solution to the wave equation. One example that you can work out on your own, not for the wave equation or for Laplace's equation with the Laplacian, is the heat equation, another partial differential equation that you will come into contact with. And this is that the first partial of u with respect to t plus some, or sorry, minus, no, make it plus, minus some c times some c times the partial of u with respect to x, the second partial, is going to equal 0. We call this the heat equation. It is the equation that describes the diffusion of heat. As a challenge to you, show that z is equal to e to the negative t sine of x over c satisfies this equation.